Hey, I'm back with another development log. Today we're going to talk about a lot of math, and I hope it doesn't turn people off, but there is a part of the game that is going to have a lot of math in the back end, at least. Some of it you can be able to guess and test your way through, but here we're going to talk about the core fundamentals of the game itself. So hopefully we're not going in too deep, but we'll see. So overall, the concept is going to be about something called link budget. A link budget is a map of all of the loss and increases in power for the entire network of signals. So starting at the satellite, the loss that occurs as the energy propagates through the air, and then the concentration of energy that is caused by the dish, and then increases in energy or voltage or potential by amplification, and then losses for filtering, and all of that results in a received power. So I should put an equation on the screen for that now, but the idea here is that we need to calculate each of these things along the way. So my goal while making this game is to make it so that I can randomly generate a satellite that has some parameters such as power, frequency, orbital height, things like what is it doing, who owns it, that sort of things, orbital inclinations. All of those items will be part of what gets randomly generated for each satellite. After you generate a satellite, when we go to an individual game tick, when we're looking at what signals we're going to receive, those ticks will have to calculate from end to end how much power is at our receiver. And then, depending on how sensitive a receiver is, we may or may not see it. For instance, if we had a satellite way out in the solar system and we had a really crappy antenna, we need to still run the math for that to understand that our antenna is not good enough to receive the signal. And then when we run that math, we get a result that's like, yeah, you can't pick it up, so we're going to not show it to the user. We need to calculate each one of those artifacts with respect to a randomly generated frequency. So to do that, I am going to model using closed formulas the shape of a filter. Now, this isn't going to be super realistic. This is going to be modeled after sort of real filters, but they're not going to be like perfect. Usually you measure these because it isn't something that is easily modeled because of lots of things that really are too deep for this game. We'll make a shape that is our filter, and it will, or amplifier, and it will have, the game will just calculate at a given frequency what is the response that the filter is going to have, or what is the response that the amplifier is going to have. In the case of this game, an amplifier and a filter are going to act exactly identically, except for one's going to increase the power when it's in its passband, and the other one's going to decrease the power when it's in the passband and decrease it more when it's in the rejection band. So in order to do that, I needed to come up with a formula for that, and I used Excel, and I'm going to jump into the Excel sheet quickly to show you kind of what's going on. So I used a r cubed or an x cubed function here, but I'm only using the negative portion. And the way I get away with that is by using a median filter. I should have the equation on the screen now, I think. But I use a median filter with the minimum value, the maximum value I want, and then the r to the third power as the shape generator. So for instance, if I change, let me see how I have these set up right now. So if I change this frequency to 1000, and I change this frequency to 800 or 600, no, 1200, let's try that, or 1500. So what it's doing now is I have a whole bunch of formulas set up to model a shape of a filter that I like, or a shape of an amplifier that I like. And in that shape, it's generating what my damping is and what my low pass frequency offset should be, and what my exponential should be. Should it be to the power of 3, to the power of 5, to the power of 7? If I change this to the power of 5, you see the drop off happens a lot more sharply. Change it to the power of 7, it happens even more sharply. 9, it drops like a rock. So usually it's like 3 or 5 that we're using. And then as I change this divisor to like 900, it becomes a lot more smooth and gentle. If I change it to 100, it becomes a lot more sharp. And you can kind of play with these powers versus this divisor to try to get you the curve that you want for that individual filter. So the way I'm actually figuring those out is I actually take a couple of points, I put them over here in this entries over here, and then I just play with the numbers until they match the 2 points that I want. I'm plotting the points, the target frequencies and the cutoff frequencies to try to give me an idea of what the shape of that filter should be. So this is how I'm coming up with some of the filter parameters. I actually used a bunch of plots from Mini Circuits, which is a low-cost RF components vendor that I used a lot of their plots to try kind of give me an idea of how much each filter should roll off or how much gain each amplifier should have. They're kind of realistic, but really it's just an approximation of real. Now, I chose the polynomial functions because effectively they're just multiplications, and computers are really good at multiplication. So it shouldn't be very laggy. I don't want to use a bunch of lookup tables because then it would take up a lot more memory. And I'm just trying to keep things simple. Speaking of simple, I also have the orbital mechanics, and those ones are going to be sine and cosine related. So the way that we're going to calculate the whole RF signal in a loop, at least initially, is to take the antenna and figure out an area for which the antenna can practically see things. That's just going to be an estimate of where the gain drops to a certain threshold. So now, after we have that number, we take each satellite in a loop and we figure out where it's at in the sky. So we run sine, cosine, and some scalars and some offsets for each satellite. I hope I have a couple of the satellite orbits on screen right now, but they're basically just a constant horizontal velocity and then sine, cosine for elevation angles. And things like geostationary satellites, they don't progress along the equator. They just go up and down if they are in an inclined orbit. But anyway, we calculate for which satellites are in view. Then when we have all the satellites that are in view, we loop through a second time and we calculate what each of the powers are after loss. And that is going to be using the free space path loss equation. And after we calculate that, we run it again and we figure out how much amplification or loss our signal or our signaling chain in the antenna has. And then finally, we compare that against our receiver to see if our receiver can pick it up. Now, longer term, and this is not programmed at all, like most of the stuff I've talked about so far is actually already written in code, but the next steps that I really want to do are start talking about the digitizer portion. So in order for you to receive a signal, you need to have not only enough sensitivity to listen for it, but you also need to have enough signal to noise ratio for you to be able to decode the signal. So even if you know what the signal should look like, if you don't have enough signal to noise ratio, you just can't decode it. So next phase, I want to figure out how I'm going to model signal to noise ratio, which may also have me doing things like secret spreading codes, which there's a thing that you can do in signal processing called adding processing gain, which is you just know what the signal should look like. Everybody knows the password for the signal. It might just be a series of ones and zeros, but we can look for the pattern of ones and zeros. After we know that the pattern's there, we can look for deviations in that pattern. So if the pattern flips back and forth in a specific way, like instead of all ones in a row, it's now all zeros and they're inverted, we can actually decode that away from noise. So we can use the principle of processing gain to increase the sensitivity of our device. I would like to start to include some of those concepts. So if we have a contract from a specific company to monitor a satellite or search for something that's missing, we can use the spreading code information to access and decode satellites that previously would have been just noise. So we could only hear the pilot tones, but we couldn't see what the data was. So for some satellites, there'll be really simple data processing that can occur, and you can find out without any help from the owning company. Or maybe you have to do some research or some other like long-term scanning and tracking of an object to figure out what the spreading code could be. Just sort of that layer of complexity where you sometimes see satellites but not decode them until you unlock something in progression. I don't know exactly how that's going to work out yet, but that's kind of where I'm at. So right now, in today's version of the game, I have broken it down into some libraries. I have the satellite generation libraries, which go through and give you the randomly generated satellites. And then I have the RF equations, which goes through and it calculates each of those parameters that we put on the screen. I haven't shared the code for how things are going to generate from the satellite perspective because I don't know if that's going to stay the same. Also, I am going to have this be procedurally generated for each seed. So the goal is that if two people use the same seeds, they should see the same satellites at the same location. And that way you can have challenges or speed runs or whatever for those particular tasks. Anyway, that is where we're at from a development perspective. I hope I didn't bore you too much with the math. These are mostly formulas that relate to real things in real life. So I think it's kind of cool. Anyway, let me know what you think. And also, one thing that I can ask from you is I have these company names. I just grabbed some random stereotypical things like space, astrostar, aero rocket, whatever, and then heavy origin. And I just grabbed two of the words and I make company names. I'm curious what you think. Should it be randomly generated companies or should I be actually like making a list of fun company names? I need to come up with 50 or so probably to make it kind of interesting, but all of those things are kind of there. Also, I'm still playing with, we're going to have some percentages trivial, some percentage easy. All of that other stuff is going to come through as I develop the game. So we're going to have some that are easy to find, some that are hard to find, and some that are like almost impossible. You really have to try to get them. And to me, that's going to be kind of the interesting thing is how do we make those end game satellites something that you actually want to get to? Because right now I understand how the mechanics are going to work, but I need to figure out how I make some of those end game things like actual cool achievements. Anyway, this is Mad Hatter and I'm out. I